This is the third section of polar coordinates, and here we're going to be using integration to find the area enclosed by a polar curve. Now to do that, the limits are the angles, the angle where we want to start measuring from. So here's a diagram here. So this would be our lower limit here, alpha. And our upper limit would be this one here. Yeah, so that'll be our upper limit. So what we need to know is basically what those values are. Yeah, where we calculate the area from and up to what. So normally these limits would have been values on the x-axis or the y-axis. So here they're actually angles, and the area, the formula that gives us the area is this: half the integral between our angle limits, r squared d theta. Okay, so we need to have the function in terms of r squared. So we might have r equals something, we need to square it. And then we're going to have stuff in terms of theta, which we need to differentiate, which we need to integrate, and we can use that to find the area. So probably the hardest part of this is working out what the limits are. Sometimes they're straightforward. And then once we've got the limits, the next thing is then squaring our equation, which may mean the use of double angle formulas. Yeah, so double angle formulae are going to be useful because you may get something you can't integrate, and then we can turn it into something you can integrate. So for example, if we ended up with cos squared theta, then we can use the double angle for cos 2 theta to make a substitution. Okay, so that'll be 2 cos squared theta minus 1, which means cos squared theta we can change to half cos 2 theta minus a half. And we can do the same if we have a sine squared theta in there. We can use the double angle, the same double angle for cos, actually the one which is 1 minus 2 sine squared theta. I mean, you can use that to make a substitution for sine squared, and that would be a half minus a half cos 2 theta. Yeah, so you may find those useful. Okay, so we want to find the area enclosed by the cardioid with this equation. Okay, so at this point we should be able to sketch these and know the values where they cross or for particular angles. So I'm going to do a dotted line there. It's not really an axis. Right, so here comes my terrible drawing of this cardioid, basically a heart shape, and the values where it's going to cross the axis. We could probably work these out actually by substituting either 0 in. So if we substitute in 0, we get 2a. If we substitute in pi over 2, we get a. If we substitute in pi, we're going to get 0. 3 pi over 2, we get a again, and then 2 pi, we get 2a. So these are the points where it crosses the axis. Now, since this is symmetrical, I'm just going to work out this, okay, and then double it. So the area times by 2 is going to give me the total area. Now, where does this start and finish? So it starts here, so that is an angle of 0, and then it finishes here, and that is an angle of pi. So those are my limits. So the equation, remember, to find the area, write this down, is half the integral between our two angle limits, r squared d theta. So we are now ready to put everything in. So we've got half, and our limits are 0 and pi. Now r squared is going to be all of this squared. So that's a squared 1 plus cos theta squared d theta. So from there, a is a constant, so that can go over to the other side. Let's stick that over there out of the way. Our limit's still 0 and pi. Here we'll expand the bracket, so we get 1 plus 2 cos theta plus cos squared theta d theta. Right, now we're going to use our double angle to change that. So just as a reminder, our double angle says that cos 2 theta is 2 cos squared theta minus 1. So if I rearrange that and divide both sides by 2, I will get cos squared theta is equivalent to half cos 2 theta plus a half. So next step, put over here half a squared between 0 and pi 1 plus 2 cos theta plus half cos 2 theta plus a half d theta. Yeah, should really put that in brackets there, so there's no confusion. We're integrating everything, not just the last thing at the end. So let's do that, half a squared. So let's integrate now. So 1 will become, well, I've got 1 plus another half. So that makes, let's just highlight that. That and that is going to make 3 over 2. So when you see me write 3 over 2 theta, you know why. So 3 over 2 theta. Then the 2 cos theta will become 2 sine theta. Then we can use the reverse chain rule to integrate the half cos 2 theta. So you integrate the outside, so that will become cos, divide by the inside, differentiate, so you need to divide by 2, half divided by 2 is a quarter, so plus a quarter sine 2 theta, so the inside of the bracket doesn't change. Okay, so our limits are 0 and pi, so now we're ready to work this out. So that will be half a squared. The first bracket I will have pi in there, so 3 over 2 pi plus 2 sine pi plus a quarter sine 2 pi minus, and then 0 in there, so 3 over 2 times by 0 plus 2 sine 0 plus a quarter sine 0. Just about got enough space. So half a squared. The first bracket inside the bracket just becomes 3 over 2 pi. The second bracket just becomes 0. Okay, so if I multiply that out, I'll get 3a squared pi over 4. Okay, now that's only half the area. We've got to times that by 2 to find the total area. And if we times that by 2, we're going to get 3a squared pi over 2. So that's going to be the area of that nice little heart shape. Okay, find the area of one loop of this equation here. So we'll start with a sketch to help us work out the limits. Now one loop is going to be this. Okay, and we want to know when or what angle does that start at and what angle does it go to. Well, I think it's fairly obvious that the start is going to be when theta equals 0. But when does it finish? Okay, well, it's going to finish when r equals 0 again. And that's going to finish when you do theta is pi over 4. Now, why is it pi over 4? Well, if r is equal to a sine 4 theta, the first time that becomes 0 after 0 is when you do a sine 4 times pi over 4. Okay, it's a bit like doing sine pi. Yeah, that's the first time. So it's not pi over 2, because that's when we're going to get negative values. The first time where it becomes 0 is when the angle is pi over 4. So we have our limits and we have our equation. So we're ready to plug it into half integral between alpha and beta of r squared d theta. So we have half the integral between 0 and pi over 4 of r squared, which is going to be this squared, for theta. So when we do that, we're going to get a squared, which will stick over that side. And then we'll get sine squared 4 theta. This we will replace using this identity. Cos 2 theta is equivalent to 1 minus 2 sine squared theta. So that means that sine squared 4 theta is going to be equivalent to a half minus a half cos 8 theta. Yeah, so that angle needs to be double. So from there we can write half a squared 0 to pi over 4, and in the sine squared 4 theta place we're going to write half minus a half cos 8 theta, which we're now going to integrate. Now, to make things even easier, what we can do is take the half that we have written here, we can take those halves to the other side because you can factorise that out, in which case then we'll have now a quarter a squared between 0 and 2 pi, and we'll have 1 minus cos 8 theta to theta. So I'll have a quarter a squared, and then here this will become theta, then the minus cos 8 theta will become minus 1/8. Yeah, we divide by the inside differentiated sine 8 theta between our limits of 0 and 2 pi. Sorry, not 2 pi, pi over 4. I don't know why I suddenly changed to 2 pi. Pi over 4, pi over 4. So now we can just substitute in a quarter a squared, and then we'll have pi over 4 minus an 1/8 sine 2 pi, or 8 times pi over 4, which is 8 pi. When we substitute in the 0, we will just end up with 0. So our final answer is going to be a squared pi over 16. Okay, let's start with part A. And the first thing that we need to do is to draw a sketch of these two equations. Okay. Now to do this, we're going to do a table of values. But since this one here is of the form R equals A, you'll remember this from a previous section, P plus Q cos theta, so it's in that form. And since the value of P is 2 and Q is 1, I can see that P is actually greater than or equal to 2 times Q. So that tells us that this is going to be egg-shaped. This is going to be an egg-shaped graph. So it's not going to be the one with the dimple in it, but we'll start with a table of values. And we want, just like before, 0, pi over 2, where it crosses like the axis is in a way, pi, 3 pi over 2. And then the 2 pi is going to take us straight back to where we start. So this is going to be for the first one, let me call it R1 and R2, and then a table for the second one. Again, same values, R2, sorry. 0, pi over 2, pi, 3 pi over 2, and then back to 2 pi. Now to do this nice and quick, I've just gone into the table function on my calculator and typed in the function, but just put x where theta is, so 2 plus cos x, and told it to start at 0, finish at 2 pi, and I've got a lovely set of values which I can just copy down. So 3, 2, 1, 2, and let me just scroll down for 2 pi, which is 3. Now I'm going to do exactly the same thing for the other equation and just use the table function on my calculator to get the values. So that gives me 5, 0, negative 5, so I'll ignore that one. 0, and the last one for 2 pi is 5. So I've got a lovely set of values here which I can use to sketch these two curves, knowing that one of them is egg-shaped. So I'll do the egg-shaped one first. So when, let's put 0, pi over 2, pi, 3 pi over 2. So when I've got 0, I'm at 3 here. Let's put 3. Pi over 2 is 2. Pi is 1. 3 pi over 2 is 2. And then I'm back to 3 again. So let's draw that. So it's going to be like this egg thing, so it flattens out like that. Okay, and let's do the same for the second one. I'll do this in a different colour. So we start at 5 when it's 0. So 5 here. At pi over 2 it's 0. Okay, so it's going to be here so we leave pi at 3 pi over 2 it's 0, and then we're back to 5 again at the end. So this is going to be going around like this, it's going to be a circle. Yeah, so that's my two sketches there. So this is the r equals 2 plus cos theta, and this one is the r equals 5 cos theta. Now part B, it says find the polar coordinates of the points of intersection of the two curves. The points of intersection are going to be these points here, and at the point of intersection the equations are equal. So at point of, or points of intersection, we will have 2 plus cos theta equal to 5 cos theta. So what we can do is we take away cos theta on both sides, so we'll be left with 4 cos theta equals 2, which means that I've got cos theta equals a half divided both sides by 4. Now that will give me a value of theta. So if I do cos inverse, let's go back to the calculator again. Cos inverse of a half, should know this one, is pi over 3. Okay, now what that gives me is, try and draw this on, it gives me this one here. Yeah. Now this is all symmetrical, there's another one down here. So I could call that negative pi over 3, or 2 pi minus pi over 3. So that other angle, I could write it down, as I said, minus pi over 3, or that's the same as 5 pi over 3. Okay. And if I were to just substitute that in, let's say into the first equation, r equals 2 plus cos, and just put the pi over 3, or negative pi over 3 into there, I will get a value of r as 5 over 2. So these points of intersection as polar coordinates, 5 over 2 pi over 3 and 5 over 2 negative pi over 3, or 5 pi over 3, whatever you like. Now part C says the exact area which lies within both curves. Now I'm just going to draw a bigger version for part C of the diagram down here, because we need to see exactly what's going on. So there's my initial line there. Let's take that off and put a dotted line there instead. And let's zoom in on this area that we're trying to find. So I've got this circle around here, and I draw that bit. Then I've got my egg round here, like this. Yeah. And the area that I'm interested in is the area in here. Yeah, so I could probably work out one of those and double it, because it's symmetrical. Now let's have a look. We have just worked out that this angle here up to there is pi over 3. Yeah. Now if I put in, so for this curve here, so for that curve there, if I put in my limits as 0 and pi over 3, so remember this is r half r squared, and that will be r2 plus cos theta all squared. Okay, that will give me the area of, let's colour it in, just this bit. Yeah, it will give me the area of just that part. I also need to add on the area of this part here. Now how do I go about finding the area of that part? Well, that red part there is actually the part of the purple curve that starts at pi over 3 and goes right to the pi over 2 line. And the purple curve is this 5 cos theta d squared. Okay, so what we need to do is to work out those two separately and then add them together. So let's do that with this one here. So half between 0 and pi over 3. We're going to expand the bracket, so we'll have 4 plus 4 cos theta plus cos squared theta, which we're going to use a substitution for, so that we can integrate it. So if I do that and make that substitution, I'll have 4 plus 4 cos theta plus half cos 2 theta cos 2 theta, okay, which I'll integrate in a minute. And if I do the same with this one down here and do this between the limits of pi over 3 and pi over 2, that should be easy enough to do, because I'm just going to square it. So I'll have 25 cos squared theta to theta, and I'll do the same thing. I'm going to change it to something that I can integrate. 3, and then I'll have 25 lots of half plus, just like before, half cos 2 theta, theta. Okay, now unfortunately I haven't got enough space to show you all the integration working, but basically once we integrate that and we integrate this with those limits and we work out the final area by adding together, we should get 43 over 12 pi plus or minus root 3. So that would be your final solution. So you probably need to just check that when you do the integration, or you could even use your calculator just to check that you do get that as the final answer. Okay, you should now be able to do exercise 5C on pages 111 to 112. So just a reminder about finding your area is half the integral between the limits r squared d theta, and the way you're going to find your limits, oops, let's just have dotted line from our initial line like this, is once we've got our curve, whatever that is, and normally these things are maybe symmetrical, is look at the angle where it starts and the angle where it finishes. So if I was working at this area, I would say, well, that alpha equals 0, my beta there equals pi, and then work out that area and double it, not forgetting that my initial lines here is on 0 and pi, and then here I have pi over 2 and 3 pi over 2.